Hi dear students, this is the 8th part of the 5th module of the subject ME 206 Fluid Machinery. In this presentation we will be discussing about the multi-stage compression. In the earlier presentations we have seen single stage compression only. Now in this presentation we will be moving on to the next topic, that is multi-stage compression. When air is required to be compressed to a very high pressure, compression is done in 2 or more stages. That is what is known as multi-stage compression. If the compression is happening in 2 or 3 stages, then it is called multi-stage. Okay. Why we go for the multi-stage compression is, as we know that there is a limitation for the compression within a single stage. If the outlet pressure required by the compressor, or the pressure to be produced by the compressor, final pressure to be produced by the compression is very high, then that compression we cannot we can't do that compression within a particular cylinder due to the high temperature rise as well as the pressure rise. So there is some limitation for the single stage compression. If the outlet pressure required is very high, then usually the compression is done in either 2 stage or multi stages. Okay, so while doing this multi stage compression, a new term you might have heard, that intercooler. So while doing the multi stage compression, in between the cylinders we will be using a heat exchanger. Actually it is called intercooler. Intercooler is introduced between the two cylinders to reduce the temperature of the air leaving the compressor at very high pressure. As we know, during the compression there will be a change in pressure, increase in pressure will be there. Correspondingly, the temperature also will be increasing. See, in a single stage compression, the air is entering at a pressure of P1 and at a temperature T1, and the air is leaving at a pressure of P2. Of course, the pressure P2 will be very much higher than that of the pressure P1, and correspondingly T2 is also greater than T1. So that means there is an increase in the temperature of the air within the cylinder during compression. So before feeding this air into the second stage of the compression, what we will do is we will be cooling that air before feeding to the second stage of compression. That is what is the purpose of the intercooler. Actually it is heat exchanger. So this air compressed within the first stage cylinder is passing through the heat exchanger to reduce the temperature of the air. Okay, that is what is known as the intercooler. So some coolant will be there. Of course, usually the atmospheric air is used as the coolant. In some other purposes we will be using some designed intercoolers also. Some designed coolants also is being used. Some cold water is also being used. That depends on the situation. Okay. Anyway, intercooler is introduced in between two cylinders to reduce the temperature of the air leaving the compressor at very high pressure. So in between each cylinder, from first, if the air is moving from first stage to second stage, it has to pass through an intercooler. From second stage to third stage, again it is moving, then again it is passing through a second intercooler connected between second cylinder and the third cylinder. Like that it happens. So if the intercooling is perfect, this word is a very important one. Perfect intercooling. If the intercooling is perfect, then the temperature of the air leaving the intercooler T3 is equal to the original inlet temperature of the air. See here, we know that if assume that there is a 2-stage compression. So first cylinder will be there for the initial compression or stage 1 compression. There is a separate second cylinder for the second stage compression. As I have already told, an intercooler is connected between these two cylinders. Okay, so the compressed air from the first cylinder will be passing through the intercooler before entering into the second cylinder for the next compression. So the air temperature of the air entering into the first cylinder, usually we have taken it as T1. So after compression in the first cylinder, the temperature rises to T2. So the air and the temperature of the air entering into the intercooler will be having that same temperature as the air leaving the first cylinder, that is T2. So air with the temperature T2 will be entering into the intercooler. So while air passes through the intercooler, it gives away its heat to the coolant since it is a heat exchanger. So what happens? The temperature of the air will be reducing. So if we are able to reduce that temperature into the initial value of the temperature that is entering into the first cylinder, that is T1 value. If we are from T2 temperature to, if we are able to reduce the temperature to T1 value by heat exchanging process within the heat exchanger, then that type of heat cooling is known as the perfect intercooling. Usually the perfect intercooling is very much difficult, but this is a somewhat we call it as ideal situation or it is an assumed situation, something like that. Okay, anyway, perfect intercooling means after leaving, the temperature of the air leaving the intercooler will have the same temperature as the air entering into the previous stage. Okay, so usually we will be discussing about two stage only. So in a simple sense we can say that the perfect intercooling means if the air leaving the intercooler have the same temperature as the air entering into the first stage of compression, then we will call it as perfect intercooler. That is T1 equal to T3, then it is called a perfect intercooler. I think the concept is clear for you. Next one is, in the case of perfect intercooling, the intermediate pressure will be P2 equal to root of P1 P3. If perfect intercooling is happening, then the intermediate pressure will be, or intermediate pressure P2 will be equal to root of P1 into P3, where P1 is the initial temperature of the air entering the first cylinder and P3 is the final temperature after the second stage compression. This is for two stage compression. If there is four stage compression, then what happens is, between 2 and, if there is 3 stage compression, then between 2 and 3 we can say that the P3, if the intermediate pressure is P3, then P3 will be equal to root of P2 into P4. That equation is valid also. Okay, anyway, for two stage compression, the initial pressure of the air entering the first stage will be P1, and with the pressure P2 the air will be leaving the first chamber or first cylinder, air will be leaving with the pressure P2. With the same pressure it is entering into the second cylinder. So the entry pressure of the air into the second cylinder will be P2 itself. That is, whatever leaving pressure the air is having through from the first cylinder will be entering into the second cylinder. Same air is entering. Pressure is not at all reduced while passing through the heat exchanger. In a heat exchanger, pressure always remains constant. So there is no reduction pressure in the heat exchanger. Only temperature is being reduced. So pressure remains constant. So the first stage, the pressure after the first stage compression will be same as the pressure entry to the second stage compression. So P2, air leaving the first stage compression will be P2, as well as pressure entering the second stage compression also will be P2. Now during the second stage compression takes place from the pressure P2 to final pressure of P3. So P3 is the final pressure and P1 is the inlet pressure and P2 is the intermediate pressure. So if the perfect intercooling is happening, then we can assume that the intermediate pressure will be P2 equal to root of P1 into P3. Anyway, we will be deriving this relation for the minimum work done. Okay, at that time we will see it. We will discuss it further. Now, next one is two-stage compression. I will explain what is happening in a two-stage compression. This is easy to explain. Here you can see the one is the inlet condition of the air into the first cylinder of the or the first compression, first part of the compression. Now you can see that this is the compression line. PV raised to N is equal constant. That is what this line says. All these are polytropic compression, I am assuming. So 1,4 is the initial compression of the air within the first stage. Okay, 1,4. So the pressure will increase from P1 to P4. Now that pressure with P4 and correspondingly you can say it as temperature T4, no problem. So it is passing, you can see a horizontal line. This line 4,2 corresponds to the intercooling process. So 1,4 is the compression within the first cylinder. Now 4,2 is the intercooling process. You can see during the intercooling process the air is passing through the heat exchanger. At that time the pressure remains constant, therefore 4,2 is a horizontal line. This is the PV diagram, so 4,2 is a horizontal line, constant pressure process. But you can see this dotted line is actually a particular common temperature line. This line stands for a particular temperature. We call it as temperature line. You might have studied in thermodynamics. Refer the PV diagram skeleton. In that everything is the graph shows the shape of every lines, like constant temperature line is marked with constant pressure line, constant volume line, everything will be marked there. So this shows the constant temperature line, this dotted one. So if the cooling is perfect, then what happens? T4 reduces to the initial inlet temperature T1. See here T1 is equal to T2 equal to T9. The reason is this is a constant temperature line. Along this line the temperature remains constant. So T1 will be equal to T2 will be, that is equal to T9. All these temperatures are same temperature. So by doing intercooling, if it is perfect, then the point 2 should be on this dotted line. So here it shows the perfect intercooling. Now P2 is the new condition of the T2 and P2. You can see P4 equal to P2 since it is a constant pressure line. So now I can say that the pressure is P2. It is okay. It was P4, but since P2 equal to P4, I can say now the pressure of the air leaving the intercooler is P2. Now with this pressure, the air will be entering for the second chamber for the second stage compression. So with the pressure of the air entering the second cylinder is P2 and corresponding temperature is T2. In that condition, air is entering to the second cylinder where it is further compressed to a final state of 3. So this is the second compression process. 2-3 is the second stage of compression. This again follows the polytropic law, PV raised to n is equal to constant. So all processes I am assuming it as polytropic compression processes for the simplicity of explanation. Okay. Now if the same, so actually what is happening here, from the pressure inlet pressure of P1 to we are compressing in 2 stage to a final pressure of P3. You can see that there is another point 5 here. So P3 equal to P5 also, since it is a horizontal line. So P3 is equal to P5, constant pressure line, P3 equal to P5. So if it is done in a single stage compression, what is happening? The compression will be from point 1 to point 5 directly along this curve. This is again a compression curve, PV raised to n is equal to constant. So compression, if it is the same compression to a initial pressure of P1 to final pressure of P5 or P3 is done in a single stage compression, then this will be the curve. If it is done in a 2-stage compression, you can see the difference. Up to 1 to 4, it is same. From 4 to 2, there is an intercooling. Then 2-3 is the second stage compression. You can see a gap in the PV diagram here, that is marked as hatched area. You can see here. So what does it mean is this much, we know that work required is directly proportional to the area under the PV diagram. So work done is area under PV diagram. So if the compression is done in single stage, area under the PV diagram means it is one area under the curve 1, 5, 6, 8, 1. This is the curve 8, 1, 5, 6, 8 is the 8, 1, 5, 6, 8 is the curve if it is done in a single stage compression. So this much area it is coming. If it is done in a 2-stage, then area reduces to 1, 4, 2, 3, 6, 8, 1. You can see this much area is excluded from the total area. So that means this much work is reduced during when we go for the multi-stage compression. The pressure ratio is same. We are compressing from P1 to P5 or P1 to P3, but the work requirement for the compression will be reduced by doing the compression in a multi-stage compression. So we can directly say that the work is saved by doing the compression in multi-stage compression. That is one advantage of multi-stage compression. And one more advantage is, see, you can see here V1 is the initial volume of the air entering into the cylinder. So the first cylinder volume should be corresponding to that of V1, at least to include all this air. So after compression, the volume is reduced to V2. You can see final, before entering into the second cylinder, the volume is V2. So V2 is somewhere here less than V1. From the graph it is clear that V2 is less than V1. So lesser volume is entering into the second cylinder. So the size of the second cylinder will be much less as compared to the first cylinder volume. So if you think about the properties of the cylinders, what happens is the first cylinder, the maximum pressure is only up to P2 or P4. So the material of the first cylinder has to withstand only this much pressure. But think about the second cylinder. Second cylinder has to withstand very much high pressure equal to P3 or P5. So the low cost material can be used to build the first cylinder, or cheap material can be utilized for the manufacturing of the first cylinder, which has to withstand only low pressures. But whereas the second cylinder, the material can be changed to withstand the high pressures. Otherwise, if the compression is done within single stage, the high quality material is to be used to make the cylinder for the entire cylinder. So in that case, we have to make a bulk cylinder with volume V1 with the high quality material. That will have some cost also. So the cost can be reduced by going for the multi-stage. That is another indirect advantage. So anyway, the direct advantage of going for multi-stage compression is the work required for the compression of air from an initial pressure to a final pressure can be reduced by going for a multi-stage compression. That is the main advantage. Okay, I think this PV diagram is very important. 1 to 4 is the first stage compression, 4 2 is the intercooling, 2 3 is the second stage compression. So 1 5 is the direct single stage compression. For the comparison purpose I have drawn this line 1 5. Actually 1 5 will not be there. 1 4 2 3 6, like this the PV diagram will be there in the two stage compression. If a further staging is there, what happens, from 3 there will be a horizontal line to 9, then from there you can we have to draw again a PV raised to n is equal to constant line for the third stage compression. From there it is coming to the horizontal line, like that it will be coming. So stage by stage, like this, from here to here it is coming horizontally, then again compression, then horizontal, again compression, again horizontal, like that it will go. Okay, if it is 3 stage you have to draw the PV diagram like that. Anyway, refer the text for the further explanations and all.